This video will take you through the calculation of the Pearson product moment correlation. First of all, a few facts about Pearson correlation. Correlation of any type really determines the degree of relationship between two variables. In the case of a Pearson coefficient, those variables are measured on a continuous scale. Both of them are measured on continuous scales. The Pearson coefficient will be a number between -1 and +1. The number indicates the strength of the relationship, but the sign tells us what type of relationship, either positive or negative. The negative relationship is also called an inverse relationship. These scatter plots represent examples of positive and negative correlation. On the left, you see a positive correlation between years of education and income. And generally speaking, the more years of education you have, the greater your income. So as years of education increases, so does income. On the right-hand side, we see a negative correlation between how many hours a week you watch television and your grade point average. And this is a negative relationship because as the number of TV hours you have a week increases, grade point average tends to decrease. So those two variables, TV watching time and grade point average, are inversely related because as the value of hours watching TV increases, the value of grade point average decreases. You can tell by glancing at both of them that the key feature is that the slope of the regression line that's drawn there for each of these graphs, on the left you have a positive slope, on the right you have a negative slope. This formula at the top represents one of several ways to calculate the Pearson correlation coefficient. In the numerator we have the sum of the products, and then the denominator is the square root of the product of the two sums of squares, the sum of squares for x variable and the sum of squares for the y variable. Returning to the numerator, which is the sum of the products, we have the formula for that here, and as you can see we have to take the sum of the cross products, the sum of the x variable times the y variable, and then from that we subtract this term here, which is the sum of the x variables times the sum of the y variables divided by how many pairs of observations we have. With Pearson correlation, we can construct both one- and two-tailed tests of the hypothesis. At the top of this page, I have the different ways that we can construct one-tailed hypothesis tests. On the left is the way that the hypotheses are constructed if we are predicting that the value of R is going to be positive. So our alternative hypothesis is that rho is greater than 0 because positive values of correlation will be greater than 0. The null hypothesis is that rho is going to be less than or equal to 0 because that encompasses a negative relationship between x and y, which we're not predicting, and a 0 relationship between x and y, which we're also not predicting. If we come over to the right-hand side, then our alternative hypothesis is that rho is less than 0. The reason for this is that negative values of rho are going to be to the left of 0. But anything equal to 0 or greater than 0 will not be consistent with what we're predicting. In this hypothesis test, we're predicting a negative relationship between x and y. Down at the bottom, where we have the two-tailed test of the hypothesis, this is very similar to hypothesis testing with z, where our alternative hypothesis is that rho is equal to some value other than 0. And our null hypothesis is that rho is equal to 0, meaning that in the population there's no relationship between x and y variables. As with any hypothesis test, we're going to compare a calculated value to a critical value of Pearson's correlation coefficient. The table that you see here comes from the back of the book, and it says critical values of Pearson correlation right there at the top. You'll also notice that at the top you have a panel of values here. When you are conducting a one-tailed test, you use that row. When you're conducting a two-tailed test, you jump down to the row below it. You have to know whether you're conducting a one-tailed or a two-tailed test. You also have to know the alpha level that's involved. Usually it's going to be 0.05, which is there for the two-tailed test and there for the one-tailed test. It might be 0.01, which is there for the one-tailed test and here for the two-tailed test. Finally, in order to determine the critical value, you need to know degrees of freedom. Degrees of freedom will be n minus 2. So in other words, if you have a two-tailed test of the hypothesis and you have 10 observations, or 10 pairs of observations rather, that gives you 9 degrees of freedom. If you have an alpha level of 0.05, that means that the critical value for rejecting the null hypothesis is going to be 0.602. This value right here. Oops, right there. 0.602. See, we have 9 degrees of freedom, a two-tailed test with an alpha level of 0.05, and we're going to come down here, and there's the value that it will be our critical value. We'll go through the steps of testing a two-tailed test of the hypothesis, which is laid out right here. We're going to have an alpha level of 0.05. Over here are the data, so we've got 6 x values and 6 corresponding y values. Our n minus 2 degrees of freedom means that we'll have 4 degrees of freedom. So first step is laying out the hypotheses, determining your critical value, which in this case is going to be 0.811, and then here are the data right here. The first thing that we need to do by our formula is calculate the sum of the products. And so in order to do that, we're going to need the sum of the cross products, which means we take each x value and multiply it by its corresponding y value. So 1 times 1 equals 1. 3 times 2 equals 6. 2 times 4 equals 8, and so on all the way down. So when we get that, we have a sum of the cross products right here, which is 57, and we're also going to need the sum of the x and y scores. Just add them together. So the sum of x is 16, the sum of y is 18. We come over here and put these values into our sum of the products formula. So here's the sum of the cross products right here, 57, and then we have the sum of x times the sum of y divided by n. We just multiply the numerator terms. Okay, that gives us 288 divided by 6. And then when we complete the problem, we have 57 minus 48 equals 9. That's our sum of the products. So I've just carried the sum of the products over from the previous page, so that value is 9. Now what I need is the sum of squares for x and the sum of squares for y, because in the correlation formula I'm going to have each of those values in the denominator, and I'm going to take the square root of the product. So here's the layout for calculating the sum of squares for x, and here it is for calculating the sum of squares for y. I need the squared x values, I need the squared y values, and I need to just add them up once I get those. Here's the formula for sum of squares. So the sum of the squared x values minus the sum of x squared divided by n. The same formula will be applied to the y values. So first, the sum of squares for x, we take 52, that's the first term. The sum of x is going to be 16, but you square it, that gives you 256, and you divide by n, which is 6. That gives a sum of squares for the x observations of 9.33. Coming down to number 8, we do the same thing for the y-scores. The sum of y squared is 70. Okay, so that's going to go there. And then the sum of y is 18, but we have to square that sum. So that gives us 324 right here, and our n is still 6. So that works out to 70 minus 54 is equal to 16. So we have the sum of the products, which was 9 from the previous slide. We have the sum of squares for y and the sum of squares for x. Doesn't matter what the order is. We've got it all under a square root sign in the denominator. And if we just work the math down, we have 9 over the square root of 149. Take the square root of 149, you have 9 divided by 12.22. And when you divide through, that gives us a correlation coefficient of 0.74. So the two steps that remain are determine the statistical decision whether or not we reject or fail to reject the null hypothesis, and either way we have to determine what that means. So remember, we had a critical value of R of 0.811, and in order to reject the null hypothesis, the value that we calculate has to be greater than this value. And because it was a two-tailed test, it could have been plus 0.811 or negative 0.811. But either way, it doesn't matter. We only were able to obtain a calculated value of correlation coefficient of 0.74, and that is not greater than the critical value. So we have to fail to reject the null hypothesis, which means our conclusion is there is no relationship between x and y. So that takes us to the end of this example of correlation. I hope this helps you refresh your memory of the steps and your understanding of how to calculate and interpret Pearson's correlation coefficient.